for mathematical optimization. Now, before starting this lecture, I would like to tell you what this lecture series is about. So, in this series, I will be discussing problems relating to unconstrained and constrained optimization and various techniques such as line search and trust region methods to solve these problems, mainly the problem of unconstrained optimization. I will be discussing the methods like line search, trust region, conjugate gradient methods, and many more techniques. Then I will discuss the problem of constraint optimization, and then we will discuss about linear programming and topics such as quadratic programming is for solving mathematical optimization problems. There is another lecture series in convex optimization if you are interested. So let's get started with this general mathematical optimization problem. So here's our problem is the problem is minimization minimize fx over the vector n-dimensional vector x which subject to some constraints. Now these constraints are divided into two parts. One of these is known as equality constraints. As you can see, ci of x is equivalent to 0 for I belongs to E, you can say, for equality constraints, and ci of x is greater than or equal to 0 for I belongs to I, or inequality constraints, you can say. So here's our objective function fx which you want to minimize with subject to constraint ci. Okay, so this was our general optimization problem. Now this problem can be defined as any problem, like maybe it may be a convex or non-convex or general non-linear optimization problem, and or it may be just some sort of linear programming. We will discuss all these topics later. Yeah, one more thing, I would not be discussing the problem of convex optimization in this lecture series. If you need to go through convex optimization, then you can, as I said earlier, you can watch my series on convex optimization. So let's start with the problem of unconstrained optimization. So general problem, the general problem of unconstrained optimization is minimize our objective function fx over our variable x, which is surely n-dimensional vector, and fx is a function which maps r into r is a and fx is assumed smooth. Okay, so let's talk about solution. Okay, for this lecture I would like to suggest you just sit back and relax, because it is just an introduction to what actually mathematical optimization is, and soon I would be posting a lecture on fields where mathematical optimization is or can be used. Like you can watch in my lecture series for machine learning, where I will use optimization problem to solve machine learning algorithms, and obviously in motion planning you can always have objective, you have to minimize your objective function for some path planning problem. We would be I will be discussing all these topics in various lecture series. Okay, so let's get started with the solution. What are the solutions? The solution for our problem are defined into two categories. One is global and other is local. There are categories for local as well, like strict local or weak local minimizer. We will tackle this problem later. Okay, so a global solution, and x star is a global minimizer of fx. F of x star is less than or equal to fx for all x belongs to domain of f. So that is it's like a unique minimizer of our function. Now other category is local solution. We are always interested to find the local minimizer of our objective function, because global minimizer is a really hard problem, and most of the literature on mathematics focuses only on the problem of local minimization. When fx is a smooth function, there are efficient you can always find efficient practical ways to identify a local minima. If fx is twice differentiable, we may find condition over x stars such that x star is a local minimizer and possibly strict local minimizer by examining our gradient of fx or Hessian of fx near the point x star or at the point x star. Okay, So before getting into real optimization problem, I would like to suggest you to note a few theorems and facts which are very necessary for any optimization technique. And one of the most important thing is Taylor's theorem. I would not be discussing the proof of this theorem here, but you can find its proof in any of the literature on like any of the calculus books. Now, this particular Taylor's theorem was like this particular equation was taken from the book Numerical Optimization by Jane Ocedal and Stephen J. Wright. So here's a theorem like f of x plus q, where q is some vector, is equivalent to f of x plus del of f of x plus tq transpose times q for some t belongs to 0 to 1. And if fx is twice differentiable, we have that you can see from here, like del of f of x plus q and is equivalent to del of f of x plus integral 0 to 1, integral is over t. And also this is very important one, like f of x plus q is equivalent to fx plus del of fx transpose q plus half of q transpose del square f of x plus tq times q, where for some t belongs to 0 to 1. So q is in the x plus q is in the vicinity of x. So okay, now here are our conditions for x star to be a local minimizer. Now I will prove necessary conditions for optimality, assuming that x star is local minimizer, and then proving facts about del of f of x star and the Hessian of f. Sorry. Now here are our conditions. Condition for x star to be a local minimizer. Now there are three conditions: first order necessary conditions, second order necessary conditions, and then second order sufficient conditions. You should be able to prove this yourself. Okay, try to prove it, and then if you really can't prove it, then you can request me for the proof of this facts. Provided my email address to you, and I will personally email, or if many people request me for the proof, then I will post it in the forum section of the website. Okay, so here is our second slide. I mean my second slide. So here's our first order necessary condition. The first order necessary condition is that the gradient should vanish at our local minimizer, provided del of f of x star is equals to 0, provided x star is local minimizer, and f should be continuously differentiable in open neighborhood of x star. Now please note one thing, that for the notation open neighborhood, I will be using this open and this n of x star. This denotes the open neighborhood of x star. Okay, where x star is our local minimizer. That is in short, local minimizer must be a stationary point. Okay, as I said, for proof you can request me if you are not able to prove, but I want you to prove it yourself. Okay, now here's what second order necessary condition. So second order necessary condition states that our